derivative of E operated onto the time derivative of this guy actually. Okay, this guy. So what would be the derivative of this inside? So this is going to be what do you call 1 minus 0. So only this part would survive actually. So you can say that this can be written as an integral from 0 to 1. Not getting into the details. The fresh derivative of E operated onto psi of V, psi of pi V minus V actually. Okay? And dt. This is what that you're going to get. So the fresh derivative operated onto the same expression, operated onto this expression actually. Okay? This is what that you can get. So now what you can do, you can take this expression, entire expression, so the fresh derivative is operating onto a bracket which is this actually. So you have to keep in view that you are operating the fresh derivative on it. So which involves d. So what I can do, okay, that I can pull this expression out of the integral by taking the maximum on the t's actually. So let me write that direct expression. So I can say that I can estimate this by the maximum of the t between 0 and 1, okay, of the norm of m of what do you call m of psi, okay, m of psi of pi v, okay, m of psi of pi v plus what do you call psi, okay, m of psi of pi v plus psi. Remember the definition, the d. So if your u is v plus psi, if your v is v plus psi and the dE operated onto u onto some what do you call v, okay, this should be equal to what? This should be equal to the integral of m of v multiplied by y dx, while the m of v is this Laplace u plus u minus u cube. Okay, this is what that was really. Now, keeping in view this formula, so if you treat okay, so keeping in view this formula, figure it out that how. So my claim is that you can rewrite this expression as this. Okay, this expression is this. Take maximum, pull it out. This integral will go away. Okay, and the norm of this fresh derivative can be estimated by the norm of m of this actually. So try to figure out this little thing actually. Okay, so I gave you, I did a similar calculation in one particular case. Okay, so this is something that you have to figure out for yourself, and you can estimate this by times this times the norm of this. You don't have to forget this actually, the psi of pi v minus v actually, because dE operated onto this expression would give me first this term, and the second term is here. Okay, so both of the terms are here. And now I can estimate. So I know already that I have estimate on this term psi of pi of v minus v, so it is c times of m of v, and you can also have an estimate on this. So this will become, you can estimate this term by m of v plus, okay, m of v plus plus constant c times psi of pi v minus v. Okay, so think about that, how you can estimate this term by this term multiplied by psi of pi v minus v and its norm actually. This is the norm of mv. Now I know about this that I can estimate this by norm of mv, and this is also norm of mv, so I can add them, and this can also be estimated by norm of mv. So if you put all the constants together, you can estimate this by some constant times the norm of m of v square. So this is another important inequality that we must say. So let me mention it explicitly. I can estimate this by c times of m of v, so the both constant will be, you can put them as a single constant. Then you can pull out the norm of m of v from both terms. This is also become norm of m of v. So some constants multiplied by norm of m of v by norm of m of v, so this will become norm of m of v square actually. So I can put all these constants together and again call them a constant c multiplied by norm of m of v square, and this is really an estimate on E of u minus gamma of xi. So I have done some jumps, you have to figure out these for yourself, okay, because it is taking a lot of time. Now what is next? The next is, we move towards the Łojasiewicz-Simon inequality. So for the gamma, now I know that you have one estimate for gamma, and this is the equation bit 2, and we also had equation number 1, which was the estimate on the gradient of the map gamma actually. So keeping in view these as two estimates, I want to now imply the Łojasiewicz-Simon inequality. So what is Łojasiewicz-Simon inequality? So I know about gamma of xi that this is analytic and the xi equal to 0 is the critical point. So by Łojasiewicz inequality there exists a sigma, a constant positive, and a number theta between 0 to what you call 1/2, okay, for which you have what? For which the gradient of gamma of xi can be estimated by the gamma of xi minus the gamma of the critical point, which is 0 raised to 1 minus theta. Okay, raised to 1 minus theta whenever, obviously, whenever xi minus 0, which is xi is less than or equal to sigma. It's Rm. Okay, it's Rm. So this is the Łojasiewicz inequality. So this, let's call this inequality 3. For now, I would like to use these 3 inequalities, 1, 2, and 3. I can use 1, 2, and 3 to prove the inequality that I want. By the way, you can always reduce these xi's in such a way that this psi of pi of this pi of v becomes an element in W2 of 0. Okay, so this is true in general for all xi's in the neighborhood of 0. But if you wish, you can sufficiently reduce them in such a way that the pi of v becomes an element of W2 of 0, so that you can apply the psi onto the pi of v. Okay, because since I want to use the inequality 3, 2, and 1, and in all of these 3 inequalities you can have the interpretations, the different interpretations for gamma. for xi. So I am choosing xi in such a way for which pi of v belongs to W2 of 0, and you know that xi is the same for all three inequalities actually. Okay, so that all three inequality holds simultaneously. Okay. Next, I want to deduce my required inequality using an element inequality. So I'm using an elementary inequality that a plus b power 1 minus theta can be estimated by the 2 times of a power 1 minus theta plus b power 1 minus theta. Okay, so using this inequality, I want to deduce the inequality that I would like. What would be the value of gamma of 0? You remember what was the value of gamma of xi? The gamma of xi was the e of psi of pi v plus psi. Okay, where the v is this I equal to 1 to m xi I phi I. Now in this, if I substitute gamma equal to 0, that means that these components xi I are 0 and v is 0. And hence psi of 0 would be 0, so I can say that this will become e of psi. So you can see that the gamma of 0 is basically e to the psi. Now I want to cleverly apply this mentioned inequality for some chosen a and b. Okay, so I want to cleverly apply for choosing a and b. So if I choose, say, a to be e of u minus xi of gamma, and b to be for the gamma of xi minus e of psi. So at one place I'll use this inequality with this e and this b. So now it's time to combine, what do you call, all these three, or use these inequalities 1, 2 and 3. Okay, so let's just start with, say for example, inequality what do you call, 1. What was the inequality 1? Remember, the inequality 1 was c multiplied by the norm of v is bigger than or equal to the gradient of gamma of xi. Okay? Now by Łojasiewicz inequality, the gradient of gamma of xi is bigger than or equal to gamma of xi minus e of psi power 1 minus theta. Okay, so this is what is the Łojasiewicz-Simon inequality. Now if I use this inequality with what do you call this inequality by choosing a as this, b as this, and what do you call this, then the a raised to 1 minus theta is going to be a plus b 1 minus theta minus b power 1 minus theta divided by 2. So I can say that this is bigger than or equal to a plus b. So what would be the sum of these both? The sum of these both is going to be e of u minus e of psi power 1 minus theta. So this is 1/2 a plus b minus 1/2 b. The b is e of u minus gamma of xi power 1 minus theta. Okay, so this is what really is going to be the case. And on this, if I, for example, apply this inequality on this, for example, if I apply this inequality, so how can I apply this inequality? So I can apply this inequality in this manner. So first of all, say, so this inequality says that E of u minus gamma of xi is less than or equal to c times of m of v square. So if you multiply this by minus 1/2, so this will become greater than or equal to minus 1/2 times c, and let's call it again c of m of v square actually. So I can say that this is bigger than or equal to, okay, this is bigger than or equal to 1/2. By the way, you need to also take the power 1 minus theta first, okay, because there is the power 1 minus theta. So this is going to be 1/2 E of u minus E of psi power 1 minus theta, okay, minus this second term will become what? First take say power 1 minus theta. So if you're going to take say power 1 minus theta here, this will become 2 times of 1 minus theta, then multiply by minus 1/2 on both sides, so this will become greater than or equal to, and c by minus 1/2, call it again c, okay, call it again c. So you're going to get minus a constant c multiplied by m of m power 2 times of 1 minus theta. So this is what that you're going to get actually. This is what that you're going to get, that c times of m of v is bigger than or equal to 2 times of 1 minus theta. Now, we are almost done, but we have to kind of reach to our key conclusion. Okay. So now I know about theta as theta is something between 0 and 1/2. Okay. So the 2 times of 1 minus theta is going to be a number that is bigger than 1. Okay. So this is a number that is, what do you say, bigger than 1. So if you do one thing, for example, so take this c and divide it by, say, both sides, okay? So take the constant c and divide by this. So you're going to get 1/2 c, let's call it again c, and minus c multiplied by c, so let's call it again c as well, okay? Now this is minus c m of v power something that is positive, and what do you call power 1. So if you wish, you can get rid of this term actually. So if you wish, you can get rid of this term. Okay? In other words, if you drop this term, the inequality will still hold actually. Okay? And what would be this inequality? M of v is bigger than or equal to c times of what do you call E of u minus E of psi, what do you call 1 minus theta actually. Okay? 1 minus theta. Now the only thing that remains now, so this is almost like what we want actually, because m of v is Laplace u plus u minus u cube. So this is almost precisely what we want actually. The only thing is we don't want this constant actually. We don't want this constant. In other words, we can get rid of this constant. This is not a big deal by making a little bit of modification in theta. Okay? How you can do it? So let's make it precisely into the form that we want actually. Okay? So since So what we can do, we can choose a sufficiently small epsilon positive such that the constant, when this constant c is multiplied by m of, not m, but e of u minus e of psi power 1 minus theta, or power minus epsilon, okay, this must be greater than or equal to 1. In other words, what I am saying, that I can choose a sufficiently small, what do you call, an epsilon for which this power epsilon is less than or equal to the constant c at, is less than or equal to, what do you call, the constant c. So in other words, I can choose an epsilon, a sufficiently small epsilon that is less than or equal to the constant c. Because if this would be the case, then you can say that your m of norm of v is bigger than or equal to e of u minus e of psi power 1, okay, you have 1 minus theta plus epsilon. 1 minus theta plus epsilon. So therefore, if I call this number theta prime, this theta minus epsilon, so if I call this number theta minus epsilon as, what do you call, theta prime, okay, then this number is still less than 1/2, so it's in our range and it's also positive, because theta is less than 1/2 and you are subtracting something positive from it, so it would be still less than 1/2 actually. So, you know, this power can be written as 1 plus, what do you call, theta prime, where the theta prime is the number between 0 and 1/2. And once you have this, you have your, what do you call, required inequality. So this is our